So hi everyone, thanks for coming. Today our speaker is Davide Gerosa from the University of Milano-Bicocca, and he will speak to us about gravitational wave populations, deeper statistics for deeper astrophysics. Please, Davide.
Hi, thanks a lot for inviting me. It's a pleasure to share some of my recent and not so recent research with you. So this talk, I don't know, we can keep it informal. So if you, I don't know, if there's something that interests you more or less than some other bits, feel free to stop me. And then if I won't get to the end, that's fine anyway. Yeah, so this is going to be kind of a cross section of some of the things that my group and I have been working on. I'm on the faculty at in Milan, in Italy, and some of the problems I've been tackling in recent years is that of gravitational wave populations, namely the art of putting events together. So gravitational wave events together, right? We detect individual black hole binaries, neutron star binaries, and so on. But we want to learn about the broader statistics, so how these things stay together, because that's where the astrophysics stay, right? That's what's going to tell us how those black holes were brought together by stars, say, and so on. And in doing that, so I started from the from the astrophysical problem. In doing that, then I got fascinated about the statistical details of the analysis and so on, and then started, because of course these days what people do, throwing in a pinch of machine learning as well into this problem and see whether that's useful or not really. All right, so so the status of gravitational wave astronomy right now is that of about 100 events. So there's about 100 events, meaning mergers of black holes and neutron stars by the LIGO Virgo detector. About 100 have been published, and there's about a few hundred more that they've detected. There's actually going to be a data release in August of this year, so yeah, basically tomorrow. The long-term prospects of the field, though, is that of an exploding number of sources, right? So these are some predictions that we cooked up now a few years ago, where the details are not important, the orders of magnitudes here are important, right? We're talking about thousands gravitational wave events in 5 years and millions in 20 years, right? Oh, sorry, and about millions in 20 years. So that's the scale of the problem, right? So we are on the verge of turning into a big data discipline. We're not right now, but we will be pretty soon. Now, when you throw in, so in any statistical process, right? If you have larger statistics, what happens is that details will emerge at the population level, right? So
Davide, I already have a question, but maybe it's too early. Maybe you'll say this later. So I can wait. But if I want to extrapolate this, so thousands in 5 years, millions in 20 years, will it go to some? Is there some bound on the number just coming from the noise of?
Depends what detector you build, right? So things like third generation detector, this Cosmic Explorer and Einstein telescope, if they will ever be built, they will detect about 10 to the 5 events per year, right? Then depends how much you can keep them alive, right? And how much money you're willing to keep machines running, I guess.
But there is no like intrinsic bound coming from just the fact that they're all together in the sky and it's hard to separate one event from the rest or something.
Not really. Not really. I mean, this is cumulative, right? I mean, as time goes by, if you increase the observation time, you're going to detect more stuff. Yeah.
Okay, thanks.
Like supernova, right? You keep on observing, you're going to observe more and more supernovas. Right.
Right. Okay.
So yeah, I was saying there are two things that are going to happen with large catalogs. So one is details emerging at the population level. So some features that are beyond detectability right now, maybe because you need, you're not really sure whether there's a peak in the mass spectrum or so on. These will emerge, typically with, a strength that is about square root of the number of events. And then the other thing that's going to happen is that if you have many events, you're going to start seeing outliers. So if if there's a rare thing, I don't know, a black hole of a mass of 150 solar mass that happens 1 in 1,000 events, before you need to see at least 1,000 before you have a decent chance of observing one, right? So more events actually means rare outliers. And often the core physics stays in the rare outliers because it tells you what's possible, right? What can stars do? And we'll see an example in a few minutes here. All right, so the outline of my talk is going to be, mainly I'll touch upon three things. Well, I'll do an introduction on the astrophysics of formation channels that you can tell me if you know all of these things, so I can skip through it. From the previous talk in the series, I felt there's more, they felt more core gravity, so I thought, I don't know, I'll do an astro introduction. But again, if you feel free to tell me to.
I think any introduction will be welcome on any topic.
I'll do an astro introduction. Then I'll describe a little bit the statistics that we use for this kind of analysis, and then I'll touch base upon something that brings everything together to some extent, which is this idea of hierarchical mergers, which is actually something I've been working on a lot in the recent past. All right, so before doing anything, it's worth asking the question, right? This is really textbook material, but can black hole binaries really make it, right? The answer is yes, because we observe them, right? But let's try and figure it out from a theoretical standpoint, right? Okay, the first equation is the quadrupole formula, basically, right? So Peter's result that tells you how the semi-major axis of the separation of a binary decreases in time. So there's a minus sign here. So that's the in spiral of a black hole binary. Now, from this equation, if you take a dt dA, do you see my cursor, by the way, if I move it? Okay, so if you take a times dt dA, that says the dimension of a time, right? So that's the typical time scale on which gravitational waves dissipate energy and angular momentum, right? This thing scales as the separation to the fourth power, which is very steep, right? So that means two things. So when a is very small, the time scale, the in-spiral time scale is absolutely tiny, right? So by the time we observe the binaries, they are so the gravitational wave emission completely dominates the in-spiral. So it's as if binaries are in complete vacuum, right? And indeed, we model them as such. So that means that for the signal that we observe, so vacuum black holes are perfect. We don't need any of the messy astrophysics and whatever, right? The other side, though, of the same coin is that when A is large, TGW becomes huge, right? That's the fourth power, right? So we can turn the argument around and ask, okay, what's the typical separation, let's call it AGW, at which the spiral time scale, TGW, is about equal to a Hubble time, so the entire lifetime of the universe. If you do this calculation, you find that this number for a stellar mass black hole, so 10 solar masses, is about 10 solar radii, right? Now, to put this number into perspective, a binary star, the separation of a binary star is 1,000 times more than that, right? So that means if you take a binary star and you hope that these two stars will form black holes, right? These black holes will be so far that they will never merge. They will take more than the entire lifetime of the universe to merge, right? So that means that relativity alone cannot explain the gravitational wave events that we see, right? So if I just hope that binaries will magically merge by gravitational waves, and they will, but they will take absolutely forever. And in practice, we'll never see it. We won't see any merger. So the answer to this problem is that we need something else that is not relativity. So we need an astrophysical mean of dissipating energy and angular momentum at large separation, such that I bring the binary down to some critical separation, which is order of 10 solar radii. And from that point on, gravitational waves can efficiently drive the in-spiral. So it's really an interplay between relativity at large separation astrophysics at large separation and relativity at small separation that plays the role. Now, conceiving plausible astrophysical scenario to do this, right? It's by far a non-trivial problem, and there have been decades of research that went into this. This is the so-called formation channel problem in gravitational wave astronomy, right? We can, simplify this to the bones with this diagram, right, if you want. So imagine you have two black holes that they ask each other, an old couple or so, have we been together for so long? So there's two ways you can do black hole binaries, right? So one is from a binary star. So you have two stars that were together as a binary. They form together and so on. One star collapses, forms a black hole. you got this mixed phase, and then the other star collapses, forms a black hole. In doing this, you need some non-trivial stellar astrophysics to decrease the separation fast enough. Or you can think about another different way of doing it, which is in a dense stellar environment, say a cluster or so, right? So these are two stars that don't know anything about each other. I mean, they live in the same environment. They're not bound, gravitationally bound to each other. They're bound to the mean field of the cluster. They separately collapse and black holes. And then these guys, once they're already black hole, they meet and form a binary. Now, the critical difference here is that on the left, these two guys have been together for all their lives, so they form together. And in this scenario on the right, they are not. Now, let me do, a quick, very quick one slide each for this idea, just to explain how it works. So in the isolated binary star case, we call it field evolution. This is because these binaries are forming the galactic fields. The strategy would be that you have a main sequence binary star, right? So this is a specific realization from back after the first detection, right? You have a binary star. These will undergo phases of stellar evolution. Like the first star will evolve into supergiant, perhaps transferring mass onto the second star. Then you go into a stage. Then, of course, one of the stars will undergo supernova explosion. And, well, you need to be careful that the supernova explosion doesn't disrupt the binaries. Otherwise, you won't have a black hole binary at the end. So that's the first challenge that you need to overcome in these models. Then you have a phase where you have a black hole. That's the first star that collapsed, and a main sequence star. Now, this main sequence star will then expand into supergiant, and people invoke what's called a common envelope phase, meaning the hydrogen envelope of this star becomes so big, it becomes as big as the separation of the binary. So what you're left with is a giant hydrogen envelope with a black hole and an helium core orbiting into it. And by dynamical friction, that's transferring the energy of the envelope into the binding energy of the binary, right? And that, in practice, decreases the binary separation. Now, people that do this calculation, they tell us that, which is not me, by the way, they tell us that this phase can decrease the binary separation by about 3 orders of magnitude, which is more or less what one needs to make emerging black holes down the line, right? Then this helium core will need to explode into supernova as well. Again, it needs to survive. Eventually, you're left with two black holes that will merge and emit gravitational waves, which will reach our detectors, and we're all happy about it. Right, so this is, if you want to do it by isolated binary star, crucially relying on some very specific pieces of stellar evolution. The other way you could do it is forget about the life of stars, just use scattering dynamics. Now, here the scenario becomes that of a globular cluster or a cluster of stars, which is a system of stars where collisions are important. Unlike, say, galaxies which are collisionless system, in the core of clusters, collisions between stars and objects in general are important. Now, don't think about billiard ball collisions, but more like gravitational scattering, right? So there are in particular, there are three-body interactions, and in a three-body object, well, two things will happen first. Sorry, I go too fast. So first, there's a dynamical friction effect that brings heavier object to sink towards the center. Now, the black holes are in general heavier than the stars because they come from the massive stars in the cluster, right? So the black holes will sink towards the center. So you're going to have a cluster of black holes in the center of clusters, which increases the density and makes many three-body interactions. Now, in a three-body interaction, now the problem is chaotic. The three-body system in Newtonian gravity is chaotic. But statistically, what can happen is that, so you have, say, a binary, so object 1, 2. This, by the way, a seminal paper made this first scattering, right? So what can happen is that you have two black holes, say 1 and 2 coming in, that meet another black hole 3. There's something funny going on and chaotic, but at the end of the day, right, these things will exchange such that there's a binary with different pairs, maybe, right? So 1 and 3, and an ejection 2. Now, statistically speaking, the guys that comes out, so 2, removes more energy than what the guy 3 has brought in, right? So statistically, the outer binary is tighter than the inner binary, right? So this is a way to tighten the binary separation. Now, this is a specific realization that you see on the right here. If you do it many, many times and with these super complicated, interactions and so on, we're talking about thousands of interactions or so. People that do this scattering calculation that tell us it's enough to actually produce black holes that will efficiently merge with sufficient rate in, say, LIGO or so, right? The core point here is that it's a completely different way of doing it. So these are the two main, if you want, formation channels. In recent years, there's been a new entries, which is that of planetary migration. And by planetary, they call it planetary because it's the same phenomena that drives planets, that moves planets in protoplanetary disks, right? Now, here the scenario is that of an AGN disk. So you have a big black hole, a supermassive black hole at the center of a galaxy, surrounded by an accretion disk of gas. And then a little binary of stellar mass black holes, say 10 plus 10 solar masses or so, embedded in the disk. There are studies on how the binary moves, whether it's formed there, it's captured there, and so on. But simulations shows that you excite these gravitational instability, these wakes here, which the net effect is to shrink the binary separation. And the energy that you inject, the negative energy that you inject into the binding energy of the binary is taken by the disk, right? So you energy via viscous interaction from the binary to the disk, right? And then what causes the shrinking the binary a little bit, eventually, bringing into, leading it to the critical separation that you need. The other interesting thing about this scenario is the potential existence of what's called migration traps. So it's not only the separation of the binary that goes down, but the center of mass of the binary moves. So these binary actually migrate through the disk. And there might be traps, meaning location in the disk where an inner binary move outwards and an outer binary move inwards. So that's a natural place to assemble many black holes and facilitate their encounter, which is something that got lots of traction in recent years or so.
Davide, can I ask a question here? So does the central supermassive black hole play any role here in the approach of these components of the binary to each other?
The structure of the disk will change a lot.
Sorry,
the details of the structure of the disk will change a lot if you change, let's say, the mass of the black hole, including then the details of the traps and how things migrate and so on. So this is really a question for the hydro people, but yeah.
Okay.
Okay. So now, we have these 2 or 3 or whatever main categories of formation channel, which are declined in a gazillion of papers and various form of ways of forming black holes. Now the point that becomes, can we tell them apart? So given the data that I collect with, say, LIGO, can I say whether a black hole binary comes from an isolated star or a cluster or so on, or maybe the fraction of black holes that comes on cluster, or things like this. Now, this is a slide that I resurrected from 2017-ish, from talks I was giving in 2017, right? And it was immensely optimistic, right? So we were going around saying that in 100 events will surely be distinguished field and cluster binaries, right? No way that's... And then we're going to use eccentricities and spins in stars have secrets because they track the supernova kicks and the tidal interaction directly and what's not and so forth, right? So the early days, in the wake of the first detection, there was an immense optimism about this problem, right? We basically had it nailed down, and we were sure that things were going. Now, in reality, that's not what happened, right? It's been 10 years of gravitational wave astronomy, and we are far from solving the formation channel problem. And we learn things along the way, right? So the astrophysical processes were modeled in an extremely simplified way, and there are actually many and unknown. Astrophysics is dirty. Relativity is nice and clean. Astrophysics is dirty, I guess. There are many intrinsic degeneracies between these channels that they end up forming more or less the same kind of events. This is also plagued by the fact that black holes are simple objects. So there's not that many things that we can measure, massive spins, maybe eccentricity, but we haven't seen it yet. So all this complicated astrophysics is really condensed into a few observable, right? Our data are heavily selection biased. So the detector doesn't see all black holes equally. And it turns out that modeling selection bias accurately is actually one of the most crucial points in this entire in this entire business. If you make a mistake there, it's very easy to get things wrong badly. The statistical problem, and that's what I want to go, it's actually challenging. And even dealing with, even just the numerical errors of the implementation turns out to be a highly non-trivial problem. And then let me end at my theoretical astrophysics. Friends are kind of creative, and predictions do change as we go, right? All right, so okay, we need to extract, and we want to extract all this wealth of information from the data. So in gravitational wave data analysis, there are kind of three levels of data processing, right? Well, there's a level 0, which is the people that actually run the interferometer. A lot of kudos to them. They're great, but it's not not something I work on. But of course, that's an amazing achievement, right? So once the data are collected, the first thing that one needs to do is to find events. This is what we call gravitational wave searches. So for the LIGO problem, LIGO observes a year of stuff, say, and an event lasts a millisecond or so, right? So the first problem is to find the few interesting milliseconds, say order 100 milliseconds in a year of nothing, of noise, right? So that's the search problem. Then once you find that interesting millisecond, you want to look, so for this search thing, you cannot go too deep into the data, otherwise you will never finish, right? So you need to go coarse pass on the data to just identify what's interesting. Once you have that, then look very deeply, which means with powerful statistical tools, into that specific stretch of data to do parameter estimation, meaning measure the masses, the spins, and the things that that individual event is telling you. Now, once you have the many events, and that's, if you want, the top of the cake, is to put those events together at the population level, which is how these many black holes, so what's the spectrum of black holes in the universe? And that's actually where the astrophysics lie. I mean, you can do some astrophysics at the single event level, but the stacking of many events is really where the big astrophysics prize stay. So, okay, let me show one equation on these 0.3 populations. This is the likelihood, the posterior that we have, right? So this is the statistical problem that we need to deal with. Okay, so here we have, so in terms of notation, theta are the single event parameters, say the masses, the spins, the redshift, the things that characterize each black hole. And lambda are some population parameters. So for instance, I don't know, I assume the black holes in the universe are distributed according to a power law, which is truncated at a given place. So for instance, the spectral index, so the inclination of the power law, as well as the mass cutoff, could be my lambdas, right? So now what I want to do is so the previous stage, so the parameter estimation gives me this. So gives me the likelihood of the individual event di given the parameters of the individual binaries. But now what I want is the posterior of the population parameter given d, not di, which is the entire set of events I'm seeing. So I want to combine the many events to go from the single event parameters to the population level parameters. And okay, so the terms here are what you think they are, right? So this is the single event likelihood. Of course, you need to put in the data somewhere, right? So this is your population model. So this is saying, given, I don't know, a population with maximum mass cutoff 50 solar masses, I expect probability of finding a mass of 10 solar masses to be this, right? This is PPOP, the population model. Then this integral is a marginalization. This is a product. We assume that all the events are independent, so they don't overlap in the same stretch of data. This is fine for now. It's not going to be a good approximation for, say, LISA. So for the LISA detector, this approximation will break down. But for LIGO, it's an excellent approximation because signals are very short compared to the data taking period. Then this pi in front is a prior. We are Bayesian and we like priors. This sigma to the minus n, that's where selection effects go in, right? So this is my population model weighted by the detection probability. So that tells me what, if I have a black hole of 10 solar masses, how probable it is that that will show up in my data above the noise, right? And I need to put that in, otherwise my inference will be biased. There's an easy way to see that. There is a toy example. Suppose that you measure one black hole of 5 solar masses and one black hole of 50 solar masses. But because of their merger frequency, the 5 solar mass black hole is 10 times harder to see. So my detector is 10 times less sensitive. If I measure 1 and 1, it wouldn't be fair to say that in nature, black holes of 5 and 50 solar masses are equally probable. I should actually say that black holes of 50 solar masses are 10 times more probable, but I only see a tenth of them, so then my observed distribution, they are equally probable, right? My inference on the astrophysical distribution should be that the 5 solar mass black holes are much, much higher, right? So this is why these guys, they are entered to the minus n. I need to counterbalance for the selection effects. If something is rarer, it means that there's more out there, right? So that's this minus n thing. Okay, so now the art becomes of analyzing things, meaning assuming a p-pop, right? Functional, simple functional form or so on. Model your detector with p-det. That's the model of your detector, how well you know your instrument. Run this inference and estimate p lambda. All right, so now one of the key things that's actually affecting my research field, and people are debating, every conference there's a discussion on this point these days, it's what is p-pop, right? So that's conceptually my prior on the universe. So basically my prior on what stars do to produce black holes. And there are, in the literature, there are mainly three things you can do, right? So option one would be to use simple parameterized functional form, power laws, Gaussians, and things like this, right? That encode some of the physical intuition of our phenomena, right? So for instance, the initial mass function of stars is more or less a power law. So it's not unreasonable to believe that the mass function of black holes will also resemble a power law, right? Things like this. So these intuitions are hard-coded, and that's prone to bad extrapolations, but they're fast. So you can easily run these things, and easily change your model and so on. Option two, that's where lots of the fancy stats is going these days, is that of non-parametric model, which has a very precise meaning in statistics. A non-parametric model is not really a model that has 0 parameters. It's a model that has countably many, so infinitely many parameters in a countable fashion, where the sampler decides how many parameters must be used. So it's you can think of it as an extremely flexible functional form, which is purely data-driven. So even the number of parameters is decided by the data. This is great. You see, oh, this is flexible and I can fit what I want. The physical interpretation of this then becomes extremely tricky, because if I tell you that, I don't know, the concentration parameters of the fourth Dirichlet process that they put onto the mass spectrum is 0.4, what's that? I mean, what astrophysics do I get out of it, right? So yeah, option three would be a direct fit to astrophysical simulations. This is an extremely informed approach, which is super model dependent, right? You're basically saying, hey, my astrophysics friend, give me your simulation, I'll feed them to the data. If those simulations are crap, my results will be crap. So it's extremely model dependent. But at the same time, if that's the state of the art in astrophysics, that's what we might want to fit to the data. It's a very reasonable approach. Very soon you realize that you cannot really run a simulation every time you need a posterior evaluation, so you somehow need to interpolate across simulations. And then quickly leads you to some deep learning machinery that you need to actually work in practice. Okay, so state of the art of this will be state of the art up to August, I guess, when the next data release is going to hit. So these are the 69 or so black hole binaries event detected at high confidence up to GWTC3. So, for instance, this plot here, you might have seen it before, but this is the spectrum of primary masses, which shows like a lower mass cutoff right here. By the way, the feature here is completely dominated by selection effects. So if you mess up your selection effects, things at 10 solar masses will go terribly bad, right? It's super important to be careful about that. Then it's more or less of a power law, so a line in log scale here, but not a straight powerful. We know now that there's a feature around 30 solar masses, right? So there's a preferential pileup of black holes around 30 solar masses. This is a distribution of mass ratio, and this is the distribution of the spins of black holes, right? Which seems to be lowish. So spins of black holes in binary seems to be around less than 0.3 or whatever, the error bars here are huge because spins are hard to measure. Right? It's weakly observable. Right. So
can I ask you a question? Can this 30 solar mass be this 30 solar mass feature can also be a selection bias that we just didn't model or don't know how to model?
I think people have checked this very, very carefully. It's a very solid feature in the data, right? People have tried with several different models and so on, and depending on the model, you find a slightly different feature, but they all find a feature around there. So from the data perspective, I would say it's extremely solid. People have checked in a million different ways, actually. So that's kind of the state of the art, where we have a pretty good handle, I want to say, on the marginal distribution. So looked at here, I looked at the mass, not mass and redshift, say, or something else. Though we're still relying on simple parameterized models. So the models that go in here are simple power laws and Gaussians and things like this, right? There are, as I was saying before, some very interesting steps into the non-parametric inference regime, which is really where I think things will be going sooner rather than later. I would say that this is about marginal results. We do have some hints about correlations. This is kind of a new frontier, and I hope that the new data release will confirm things and maybe tell us something new. So, for instance, one of the obvious correlations that the astrophysicists predict is that the mass spectrum should evolve with the redshift. Masses of black holes should be different at higher redshift, and the reason is that the metallicity of the galaxy of the universe is lower at lower redshift, which creates more massive black holes. So we should expect black holes that are far away to be bigger and more massive, right? We're not really seeing that. There's no evidence right now in the data that the black hole mass spectrum evolves with redshift, though we have a few events. So that's one of the things to look for. The one correlation that was found is this one, which is between the mass ratio and the so-called effective spin of the binary, which is a weird combination of the two spins of the black holes, which turns out to be the lowest order post-Newtonian term, spinning post-Newtonian term. So that's the easier thing to measure.
Sorry, Davide, I just want to say that some of us have an alarm here.
Oh, shit.
Yeah,
Okay.
so we can try to continue actually. But yeah, people. Okay, I just wanted to say it. I'll try to continue actually in my shelter. Okay.
Should we pause for 15 minutes maybe and go back?
No, maybe you want to pause for about 1 minute so people can orient themselves towards the shelter.
Yeah.
And
Okay,
then
let's
continue
pause for
once
a
people
minute,
are
and then continue.
once people are settled down.
Let me know. I'll stay here.
Okay, I'll let you know. Sorry about that.
Yeah. So it's just up north, right?
I'm not sure I'm up north. I don't know what's happening in other regions. I saw that Amos also went. So
Okay, it's probably up north.
at least in the north, but sorry about this.
Not your fault.
Yeah. Okay, I would suggest to continue, and I made also Opik the co-host, so in case I am disconnected, take over Opik, please. All right.
As you guys prefer. I mean, I have absolutely no problem in interrupting this, or I'm happy to keep going if that helps. But as you,
Yeah, this is our daily dose
Yeah,
of
please.
normalcy.
Davide, please do. Please do.
okay,
We're fine. We're fine.
really, all right.
Okay.
Yeah, sorry, it's a bit weird. So, yeah, to give a talk about science when people, okay.
We're good. We're good. You're making us feel normal. Go ahead, please.
Thanks for saying that. Okay, so okay. Let me get back into back in the mindset of giving a talk. All right. So I was saying. So we looked at marginals, and then we have a pretty good angle on that. The correlation problem is kind of the next frontier. And the first good hint of this, so we expect the mass to evolve with redshift, but the first thing that was found is actually something that was very unexpected, which is a correlation between the mass ratio and the so-called effective spin, which is a combination of the spin of the two black holes. So this was first discovered a few years ago now, and then confirmed with more data later, confirmed with different statistics. So they tried with different statistical methods or so. And the reason here is that it's extremely puzzling, and there's basically no astrophysical model that could explain this satisfactorily. I have a paper on this, and it's not satisfactory at all, right? And I don't think there's a good solution for why. So what the data are telling us is that black holes that have and they're more unequal spin more, right? They're more fastly rotating, and this is basically no astrophysical model predicts, at least not in an easy way. So you need something convoluted to make this, which is, I don't know, a surprise, but also an exciting thing to see, right? So we're at the stage where data are telling us something that we didn't know before, which is, for a field of science, is pretty exciting, I want to say, right? All right.
So on this point, would there not be a selection bias? If you have an unequal mass, then the overall signal will be weaker because the smaller mass is smaller. And then a higher effective spin means you'll actually have a longer in spiral. Maybe there's some observation selection bias here.
No, so this was, of course, the first thought, and even from the first paper, there's a careful analysis of this. And again, several people have checked, myself included. No, selection effects are carefully taken into account here. Waveform biases are not. So but that's a small effect. So potentially there's a systematic bias, which, who knows, but they're small, and the statistical selection effects are in these analyses. So there, I'm very confident excluding it for, actually. I think it's real. I think it's there in the data, honestly. Yeah. Okay. Then, okay, so this is one of the surprises that the data are telling us, right? So how about, comparing with, so, okay, let's move on. But another solid prediction, or maybe solid, that comes out of stars is the following, is that of gaps. So this is a plot, it's a bit outdated, but this is a plot of so on the x-axis here is the zero-age main sequence mass of a star. That's single stars, forget about binaries, right? This is about the collapse of stars into black holes. And this is the mass of the compact object on the y-axis, right? And you see that there are gaps in the mass spectrum. So we expect that, these guys from 1 to 1.4 or whatever solar masses, those are the neutron stars. Then there might be nothing, or now we have some events or so, but, there might be at least fewer events down here, which is what we call the lower mass gaps. Then we have another set of objects, which are the black holes that we all know and love. And then there's nothing here, up here. So with the cap here, there's about 50 solar masses. So what our astrophysics friends are telling us is that it's very hard for stars to produce black holes that are much more massive than 50 solar masses. And the reason is the following. It's called pair instabilities in supernova. So what happens here is that, so in this plot here, on the x-axis, this is the CO, the carbon-oxygen, the mass of the carbon-oxygen core before collapse, and this is the mass of the black hole. So at low masses, this is kind of linear, which kind of makes sense, right? The more material you have, the bigger the black hole. But then there's this thing that happens here. So what happens in this regime is where the carbon-oxygen mass is about 45 solar masses. The temperature in the star is so high, in the core of the star, it's high enough that photons spontaneously decay into electron-positron pair. Now, if you do that, you're removing pressure, you're removing photons from the star, so the radiation pressure from the star drops, and the core therefore contracts a little bit. If the core contracts, it heats up. If the temperature goes up, you produce more electron-positron pairs and so on and so forth, right? So the temperature keeps on going up until you reach the ignition temperature of the oxygen. So that's like the oxygen in the star like flares up, like lighting up a fire or so, right? So at that temperature, the entire star like burns in fire without producing a black hole at the end, right? There's no remnant left, which is why the mass of the black hole in this plot like goes to basically zero, right? So the entire star is gone into this pair instability supernova process, right? Now, people that do these calculations, right, they tell us that basically black holes are forbidden about or kind of 50 solar masses. Then people do papers and say, oh, no, this is maybe not 50, might be 55, or but if you do this with stellar evolution, we actually push it to 60 and whatever, right? But that's a detail. In general, black holes, so stars cannot produce black holes that are arbitrarily large. Now, there are problems with the stellar collapse at some point, right? And whether we can bypass stars entirely, it's one of the points that I'll try to address. Now, this was what we thought, and then this event happened. So 1905-21, this is now 6 years old, or the impossible black hole. So this is a signal, it's a extremely short signal, and the reason why short is very high masses. And the masses of these guys was detected in 3 detectors. The masses of these guys are about 65 and 85 solar masses, which is right where black holes shouldn't exist if we trust the stellar evolution theory, right? So these 85 solar mass black holes was one of the, at the time, a huge surprise, and actually sparked, I don't know how many hundreds of papers that were devoted to this event and explaining how on Earth we see a black hole of 85 solar masses. One of the ideas I've been personally working on, and I still think, and it's somehow widely recognized to be one of the most viable way of doing it, is that of black hole generations. So suppose that you have, I don't know, stars appear, they collapse and form black holes, and that's the we see. Now, these first generation black holes are bound by the pair instability limit. So each of them cannot be more than about 50 or so solar masses. But suppose that you do something else instead, right? They have some black holes, stars appear, they form first generation black hole, each below 50 solar masses. These 2 black holes merge into a second generation black hole that now can easily have 100 solar masses. I'm making this with black holes, right? It's not with stars. And then these 2 100 solar mass black holes meet and merge. And that's the event that I see. Now, that's an easy and cheap way to avoid the pair instability mass limit, right? So this black hole generations idea is actually orthogonal to the usual field and cluster debate, because I'm just saying I need to assemble black hole, not how. That said, it's a complementary, because of course, to assemble black holes, you need an environment which is dense enough to do it, right? So this is a thing that relies on relativity, because it's about mergers and so on, that can tell you something about the astrophysics, which is why I think it's actually pretty exciting. So I've been dedicated some time to this, especially back in 2017-ish or so, we rediscovered older prediction about this 0.7 magic number for the speeds. Okay, the physics goes as follows. So in a black hole merger, you have the orbital momentum of the binary L, S1 and S2, there are 2 spins, and after the merger, that's converted into the spin of the final black hole. Now, if, say, the spins are aligned, there's this thing called the orbital end gap effect, where aligned binaries orbit, they have a few more orbits, so they tighten a bit more before plunging. Now, if there are a few more orbits, the gravitational signal is longer, but that also means that they plunge from closer in. So L, the orbital momentum, is a bit smaller. So you have to do L plus S1 plus S2, but L is a bit smaller. Now, the opposite case would be anti-aligned spins. Now, these guys, they orbit for less, so they plunge from afar. So L is longer. It's true that you need to do L minus S1 minus S2 now for anti-aligned binaries, but L is much longer. So these 2 effects counterbalance each other to the point that the final spin is more or less always the same. Heart centered at about 0.7. So this is a specific. There's a specific realization of this idea here, here on the right, where I have first generation black hole spins, which are flat, uniform, or so on. And already by the second generation, the spin of that second generation black hole is very, very peaked at about 0.7. So we realized this back in 2017, and then 1905-21 happened and so on. And this was enough. So this realization then generated an explosion of new prediction here, right? So this is another of these exercises where we took, so blue here, it's a set of events compatible with the gravitational wave events we observed. And these are the distribution of their merger remnant. And indeed, their merger remnant have higher masses, so M here. So they leak into this pairing stability gap, right? And considerably higher spin. So the spin distribution is very, very, very highly peaked, right at 0.7. And well, we summarized all of these in a dedicated review a few years ago. But really, it's now one of the leading explanations, at least for 1905-21, possibly for another event I've been working on, and perhaps even produces some of the correlations that we are observing. So I think it's been a really fruitful way of thinking about the black hole problem, this hierarchical mergers idea. Right, so this is still from our summary of where these hierarchical black hole mergers can come from, and why basically also these gray things are ways that people have proposed to form black holes, and they all contribute to the first generation subpopulation, but only a few of them actually contribute to this hierarchical subpopulation. And if that's easy to identify, perhaps because of their high spins, that means constraining really what fraction of black holes are coming from a subset of these formation channels, which would be pretty exciting. So really, this hierarchical mergers idea could be a subset of black holes with very well defined properties, large mass and spins at 0.7, that will track a specific subset of the place of the astrophysical places where black holes are formed. Which, if that's true, that would be pretty exciting. Right. So as any good theorist, right? So if you're a theorist, whenever you have an idea, first thing you have to do is try and kill it, right? And see when it doesn't work. So we asked, so this was a paper a few years ago, when we asked ourselves, okay, what black hole should I observe to conclude that that's not a hierarchical mergers, right? And the answer is, in retrospect, obvious, but it wasn't obvious at the time, is that of high masses but low spin. So here in this plot, we have masses and spins again, and we tried with a variety of models, we tried to easy and complicated things and whatever in terms of this hierarchical mergers idea. And there's this region, above 50 and less than 0.2 in spins and whatever, which is kind of empty, right? So that's to say that if you observe an event in this gray region, that's going to be tough. It's going to be tough because normal stellar evolution cannot do it, and hierarchical merger because the mass is too high, and hierarchical mergers also cannot do it because the spin is too low. And there we need something else, right? And again, the astrophysicists are very creative, so people have produced ways of actually putting black holes in that doubly forbidden region, as I would like to call it. But that becomes more and more, right? We're going into probing more and more specific phenomena here, and I have a list on this on these slides. Right, so kill your ideas. That's, I guess, a good lesson for everyone. Okay, then what we try to do, the idea, and say it here, was, maybe this hierarchical merger subpopulation is easy to extract from the data. Maybe you immediately enter a problem here, which is that the merger process, so suppose that now you want to build back in the statistics part, right, go back to stats, suppose that now you want to build a p-pop that contains a subpopulation of hierarchical mergers. Now, this subpopulation is the merger product of the first population, and this process, even if you model it with, fitting formulas to an R simulation or so on, is going to make your population non-analytic, right? The distribution, the PDF of the distribution, it's quickly becoming non-analytic. I mean, what do you do? So that's a perfect test bed for a p-pop that is not analytic and therefore cannot be evaluated at runtime whenever you want. So if p-pop is a Gaussian or a power law, every time I need to sample this posterior, I just sample a power law. That's trivial, right? If now p-pop is something that it's not analytic, that I have based on samples, then becomes considerably harder. The computational problem becomes considerably harder. And we use precisely this hierarchical mergers idea to showcase how deep learning can actually be useful in this problem, which is, where is it? So which is these lines here, right? So what we are doing now is to consistently, so we generate a population of black holes, then we generate their merger product, and then we mix a fraction of those merger product to the initial population. So I have a set of black holes that are contaminated, if you want, by these hierarchical mergers, right? Now, the computational problem is that the population becomes non-analytic, and here we've been fitting it with a neural network. It's a combination of FFT-based KVEs for those who know, well, for those who are practitioners with these techniques, and fully connected neural network to tackle the regression problem with full selection effect modeling and nested sampling down the line to actually sample the final posterior. And so when you run then the model finds what you actually expect. So this plot here shows the total mass spectrum in blue and the mass spectrum of only the first generation black holes. And as you expect, the FITS wants to put the first generation black holes at low masses and use the higher generation black holes to explain the tail at large masses, which is exactly what you think it should happen, right? So it was great to see. The model here, I have to say, it's very simplified. It's kind of a toy model. We are more interested in testing the deep learning side of things. So the astrophysics is not top of the notch, right? But it's going where it should be going. And if you trust these things, so this plot here, if you look at the left one, histograms, this is the fraction of first generation black holes in the catalog. That's about 75%. So we should expect that about 25% or so of the black holes could be of higher generation, which I don't personally trust the number by itself because of the simplicities that goes into the astrophysical models, but the methodology, I think it's pretty solid once you throw in more accurate simulations to this. Okay, this is the full pipeline. If you're curious about how we're actually doing things, we start from a set of training simulations. So we run these toy astrophysical simulations across the population parameter space lambda. We sample them to simulate events. And then we simulate the actual things that you measure with their error bars, this theta. And then we go down deep learning in 3-way. From the simulated events, we deep learn the branching ratio. That's what's needed to do these plots at the bottom. This is the big neural network. Then we use deep learning for the detection probability to learn about what our detector is doing. And this one to the right is the big neural network that tackles the population problem. All these things goes at the bottom, where via hierarchical Bayesian statistics, which is the big likelihood I was showing before, throwing in gravitational-wave data, of course, the data needs to come in at some point, we go to the astrophysics, which is what we care about. Okay, so before I finish, the last thing I want to say is this is one of the things that I've been working on with the students semi-recently, and we're now working on a follow-up, is to try and go back to the symmetry breaking problem, right? So I would say one of the big surprises that came out of gravitational wave data is this correlation between the mass ratio and the effective spin, right? And because of I had all this hierarchical mergers idea in my mind, I thought, okay, well, can they do it, right? Well, maybe. So hierarchical mergers will make small mass ratio. That's if you pair unequal generations, right? So if you have a field of black holes of 10 solar masses, they will merge. There will be a 20 solar mass black holes. If that meets a 10 solar mass black hole from the rest of the population, will naturally do an 0.5 mass ratio event. So you actually go down in this plot. Hierarchical mergers will also make big spins, right? Which is great. Now, that doesn't explain the full picture, right? Because so in this mindset, you might have that the black holes from star explains the guys up here. The black holes from other black holes will explain the ones down here. But that doesn't explain why you don't see any negative chi-effective. Chi-effective has to do with the cosines of the inclination, right? So hierarchical mergers, if you assemble them naively, will produce equally positive and negative chi-effective, larger positive and larger negative, right? So it's funny that this area is full and this one is not, right? So there's black holes here, but not there. And what we thought about with the student here was that, well, what this is saying is that there must be some form of preferential direction, right? Something that must break the isotropy with which black holes are assembled. So we started thinking that maybe the symmetry of the environment is the secret, right? And we have a toy, again, I like toy models for everything here, but we have yet another toy model where, you know, your field binaries, where spins are more or less aligned, will produce something like these gray points here. If you put black holes together in cluster, so in a spherically symmetric kind of fashion, you would equally produce positive and negative black holes. If you instead, okay, what if I put things together axisymmetric, right? After spherically symmetric, the next simplest thing you can do is axisymmetry. So if I put things together in an axisymmetric fashion, but with both progress and retrograde orbits, right? I do produce these two wings, this yellow thing. If I instead only put in via prograde orbits, which kind of makes sense if you buy this planetary migration mindset, right? Where black holes are assembled in these surrounding supermassive black holes and so on. If you read papers in this, so here's some exploration down here, they do say that prograde orbits are actually preferred. If you do this, that kills the left wing in this plot, leaving you only the right wing, which goes in the direction of what we are observing. And we did a full fit, and actually, if you mix the gray and the red population with some mixing fracture, you get a decent exploration of the data. Again, I'm fine-tuning things here. I'm the first one to admit it, but I don't know. Maybe the fact that this asymmetry in this plot here is actually telling us something about the asymmetry or the symmetry of the environment, which is, I would argue, definitely in more agreement with axisymmetric environment than spherically symmetric environment. Which, I mean, it's already probing the symmetry of the environment where black holes merge, which is, if you say it like that, it's pretty cool, despite all the limitations of this problem. Okay, so I think that's kind of finishes what I want to say. So hopefully there was, I don't know, a cross-section of some of the things I'm interested in. There's going to be more very, very soon, right? So this is a plot of, this is not a projection, this is the plot of the actual set of events, right? O3A and O3B are what we have right now. So these are the things that have been published. This gray line going into O4 are the triggers. So things that have been released to the public as interesting stretches of data. Some of them will be confirmed, some of them might be not. So maybe the final number is a bit less, but O4A is going to be released in August. So there's a lot, and it's going to basically double the size of the catalog, right? It's going to be from 100 to about 200 events. Right, so in August, we'll have twice as many events we have right now. Now, this looks like a lot. In statistics, things tend to go as the square root of the number of things that you measure. So that's going to be a square root of 2 improvement. So a 50% improvement, say, give or take, on the measurements that we have right now, which is pretty good, I want to say. And let me say again, and then we have O4B, and now they've extended it to O4C as well. So really the next few years are going to be nice, right? We're going to see, we're going to have the data, which is really great. Let me say again what I said at the beginning, that large statistics means details emerging at the population level. So if there's a subpopulation of hierarchical mergers, the peak at 30 solar masses, the spin distribution, correlations, and so on, this is where things are going. But many events will also mean rare outliers. So the one event that has 150 solar masses that will happen 1 every 1,000 gravitational wave events, that's where we are going, right? And already from 1905-21, rare events are telling us something. All the pair instability business and so on are really telling us a lot about, because they probe the extreme, right? They tell us what's possible. So yeah, these are the two things that will happen sooner rather than later, in my opinion. And that's all. Hope you're safe.
Thank you, Davide, for a very interesting talk. Okay, questions? Well, so maybe I'll start if there is no question at the moment. So so when do you expect us to begin to have like redshift information on the population, the redshift dependence, and what's the first thing that we can find out from that astrophysically? What
So,
will this
so I didn't have a plot
inform
here.
us about?
I didn't have a plot. We do have some redshift information, right? We do know that the rate of black holes is higher at higher redshift. It increases with redshift, right? This is very much expected because the star formation rate increases with redshift, though not indefinitely. So the star formation rate peaks at about redshift equal 2. We've not seen black holes out there yet. So one of the things that's the big price of, say, third generation detector is to push you to higher redshift to see the peak of the star formation rate, and then eventually probe the high redshift regime, say redshift 10 or so, where black holes cannot be formed from stars because there are no stars at redshift 10, right? So if you see a black hole at redshift 10, there are no stars there. That's pretty exciting. You need to go into primordial black holes and cosmology and the cool stuff, right? So that would be a region which is free from the messy astrophysics, which is messy, right? So we do have some information. We see that the rate increases with redshift, but we're not at the peak of the star formation rate yet. That's going to take a while though, because it's a redshift 2 and then it doesn't drop to 0. So that's going to take a bit. Something that will happen sooner, I think, maybe already in August. I don't know what the LIGO folks have in their pockets right now, is correlation between mass and redshift. And that I've seen it, I said it before, but at higher redshift, the universe had lower metallicity, so more hydrogen and helium compared to metals, which is everything else for the astronomers, right? So lower metallicity means lower stellar winds, which means higher black hole masses. So we expect that black holes at high redshift should also be more massive, right? We don't have evidence in the data so far. So people that have looked for mass redshift correlation, the errors are what they are, and so there's no evidence right now, but that's, I think, is the first thing that we will see, and it's very much expected. I want to say, actually, if we don't see it in a while, that would be very surprising, and we need to think very hard on why that's not the case. Because we know we measure the metallicity content of galaxies at high redshift.
Great, thanks. Any other questions? All right, if there are none, then let's thank Davide again for a great talk.
Thank you.
I'll stop the recording.
I hope you're all safe.